In the diffraction experiment, we can think of the waves as probability waves for a particle. If the ratio of the wavelength to the width of the opening is large, the diffraction wave is spread out at the detector, meaning the particle has a probability to hit the screen over a wider area. In order for the particle to hit the detector over a wider range, it must be moving laterally with more momentum. Thus, the particle's position is restricted to pass through the narrow opening of length L, which results in a wider diffraction or more sideways momentum. If the ratio of the wavelength to the width of the opening is small, the particle hits the detector over a much narrower region. We know the particle goes through the opening, which has a length L. If the particle is detected over a more narrow region, it has less lateral momentum, since it doesn't deviate too far. Thus, if the particle goes through a wider opening of length L, it results in a narrower diffraction having less sideways momentum. It turns out there's a relationship between the length of the opening L and the particle's momentum. This relationship captures the essence of a universal law called the uncertainty principle. And we can write it down as delta x times delta p is greater than or equal to Planck's constant, h, 6.6 times 10 to the power of minus 34 joule seconds, where delta x is the uncertainty in the position of a particle, and delta p is the uncertainty in the particle's momentum. In other words, between delta x and delta p, there must be some minimum level of uncertainty. We can't know both values to any degree of accuracy. It doesn't matter what equipment we use or how we set up the experiment. In every situation, there is always a trade-off between the uncertainty in a particle's position versus its momentum. It's a principle of nature itself.